Let's go up a level just for a second. What have we built so far? Simple objects, the idea of iteration. For and while loops is a way of doing particular kinds of computations, reusing the same piece of code over and over again. And now we've introduced the idea of functions as a way of capturing that code. That puts us in a position to introduce another really big idea in computer science, and that's the notion of recursion. I'm going to show you an example of recursion in a second, but let me give you the sense of what recursion is about. Recursion is going to be a nice way to design solutions to problems by breaking it up into pieces that I can reuse. Divide and conquer, or decrease and conquer, are words that we're going to use around here. And it's in particular a programming technique where inside of the function it calls itself. So I'm going to define a function, say f. And inside the body of the function, I'm actually going to call f. Now this is the kind of thing that in high school geometry class you could get into trouble, right? You don't define something in terms of itself. But in recursion, as long as we don't set up an infinite loop, we don't call it infinite numbers of times, we're fine. And so we're going to see in recursion that as long as we have one or more base cases that are really easy to solve and can be solved directly, then I can solve a problem by reducing it to a solution to a simpler version of the same problem until I get down to a simple base case. That notion of recursion is going to nicely amplify iteration. It's going to give us a much more simple way of thinking about how to break problems up into simple pieces. And so we're going to spend the next portion of this lecture just looking at different ways of using recursion. If you think about iterative algorithms to set the stage for recursion, what do we have? They're basically looping constructs. And they are captured by the idea of having a set of state variables that update each time through the loop. So I've got a while loop or a for loop. In the case of a while loop, we talked about setting up the variable outside the loop, inside the loop changing it, usually decreasing it, until I got down to a state where I'm done, and then returning a value. That's what an iterative algorithm does. So here's a simple example to think about that. Suppose I wanted to do integer multiplication. And yeah, I know that already happens in Python, but I want to use it as an example. I could think about multiplying a by b as the same thing as adding a to itself b times. So it's really, if you like, a plus, I've got b of those. That's the same thing as a times b. Iteratively, I would solve this by saying, I'm going to capture the state of the computation with an iteration variable. Let's call it I. I'm going to start it off at b because I've got b additions to do. And a current state of the computation, I'm going to call it result. And I'll start that off at 0. And then my iteration is to simply, at each stage, do one more addition and reduce that variable by 1, that iteration variable by 1. And down here at the bottom is a function to do that. Multiplication iterative takes in two parameters, a and b. It sets result when I call it to 0. And then it runs the iteration I'd expect, that little loop right here, that says as long as b is bigger than 0, I'm going to change result by adding a to it. I'm going to reduce b by 1, and I'm going to keep doing that until b gets down to 0, in which case I'm going to return the result. Cool. Nice iterative way of trying to make that happen. There's the iteration. There's how I'm changing the computation. There's where I'm changing the iteration variable. And when I'm done, I'm simply going to return the result. Okay, I'm not going to run it. I encourage you to try it yourself, but you'll see that it actually does the multiplication I'd expect. With that in mind, now let's look at a recursive solution to this problem. And here's the way about thinking about this idea of doing successive additions to compute multiplication recursively. Again, a times b is adding a to itself b times. But I could think of that as saying that's the same as adding a to itself b minus 1 times. Okay, you say, that sounds like semantics. It is, but it's an important point. Because what's this? That's just a multiplied by b minus 1. Ooh, that's cool. Because now I've taken a problem and I've reduced it to a simpler version of the same problem, plus an operation I know how to do. Okay, what's a times b minus 1? Oh, I know how to do that. That is just a plus a times b minus 2. I could do exactly the same reduction. And I could keep unwinding this computation. I need to stop somewhere. I could keep unwinding this computation until I get down to a base case, something that I know how to do. And what's the base case? When b is equal to 1, the answer is just a. And boy, that's nice, because there's a recursive implementation of multiplication. Inside the body it says, if b is equal to 1, that's my base case, just return a. Otherwise, return whatever I get by adding a to doing the same thing, but on a slightly smaller problem, multiplying a times b minus 1. And that will again call itself until we get unwound down to the level that we want to get to. There's the recursive step. And that's a standard form for a recursive function and is a really elegant way of thinking about how to solve this problem. I could do the same thing. Let's think about computing factorial. Factorial, written in mathematically as n followed by an exclamation point, is the product of n times n minus 1 times n minus 2 all the way down to 1, where n is a positive integer. If I wanted to solve this problem, I could say, so what values, or for what values do I actually know factorial? And that's easy. If n is 1, factorial of 1 is just 1. There's my base case and the value I want to return. How would I return it? Well, just as I did with the multiplication case, n factorial is the same as multiplying n by n minus 1 factorial. So there's the recursive step. And I've just written the body of code for something that would be a definition for factorial or fact. What you're seeing here is a pattern, and this is the idea of a recursive function. Break it down into a smaller version of the same problem, plus some operations I want to do, and figure out when can I stop breaking it down into smaller versions of the same problem because I know how to compute it directly. In the case of factorial, when I get down to a factorial of 1. With that in mind, let's deal with something that may be puzzling you, which is how in the world does the computer know when to stop unwinding this? And how does the computer know which versions of the function, of the parameters to the function to use? I'm calling fact of n. How does it know which version of n to use? We've already kind of seen it, but let's walk it through. So here's my definition of fact. Fact of n is if n is equal to 1, return 1. Otherwise, return n times fact of n minus 1. And I'm going to call it on a value of 4, and I want to print out the result of that. I'm going to do this reasonably quickly because you've seen these pieces before, but let's look at what happens. When I define fact in that global scope, I create a binding of fact to some code. Hasn't been run yet. And now I'm ready to run it by actually calling it on print of fact 4. Okay, here we go. I got to call fact of 4. Fact creates a new scope inside of which n is bound to 4. And relative to that, it's going to evaluate the body of the procedure. It says, is n equal to 1? No, it's equal to 4 here. So I go to the else clause, which says return n times fact of n minus 1. Aha! I got to call fact again. I know I want to return fact, or 4 times fact of 3. That's the value of n minus 1. But I got to call fact. Great. It creates a new frame, inside of which the formal parameter, n up here, is bound to 3. And relative to that, it does exactly the same thing. So I'm now going to go faster. Is 3 equal to 1? No. So I'm going to return 3 times calling fact on n minus 1, which is 2. That calls a new frame. There's the binding for n. N still not equal to 1. I'm going to again go to the return clause or the else clause that says return 2, which is the value of n times fact of n minus 1, which is 1. And that calls one more frame. And aren't you glad I didn't do fact of 64? Almost done. In that frame, I now say, is n equal to 1? Great, it is. And so in that case, I know that's the expression I want to call. And it says, return 1. Where does that go? I'm returning 1 to the person who asked for it. And that was that call to fact. That's great because now that expression says return 2 times 1, the value returned by that call to fact. And who asked for that? Right there. That reduces to return 3 times 2, which reduces that one to return 4 times 6, which prints out 24. And I'm done. So you can see the computer with these scoped nested scopes, these nested frames, nicely knows exactly where to get values in order to do the computation. And therefore, the computer knows to stop at the right time. I've just said that. Simply going to put the slide up so you can see it. Each recursive call creates its own scope. Bindings of variables in a scope are not changed by the recursive call, and the flow of control passes back to the previous scope because that was the person who asked for that function call as we did it. And therefore, I'm going to be able to use exactly the same variable name. I need to because that's the formal parameter of the function, but it's always done in a different scope, and therefore it's always clear which version I'm using when I'm calling the body of the procedure. This leaves us then with this nice comparison between iteration and recursion. Both of these pieces of code do exactly the same thing in terms of what they compute. How they do it is done differently. I'll let you decide your own style. Personally, I like recursion better. I think it's more intuitive. I don't have to remember to set up a parameter variable before I start things. I don't have to worry about dealing with all those pieces. I can make them a little different. In this case, I've changed it slightly to use range rather than setting up the iteration variable. But I personally find the right-hand side easier to look at because I can easily see where the recursive call is. From the programmer's point of view, recursion may be more efficient. From the computer's point of view, it may not be as efficient, and we'll see that. But basically the idea is each of these things does the same thing. You get to decide which one you want to use.